good morning, everybody, and welcome to this presentation. I hope everybody can see my screen, and I'm very happy that already so many people are gathered. I would like to welcome you to this webinar and would like to encourage you. If you have questions, please don't hesitate to raise them in the chat or raise your hands to ask them. I will also try to answer them in between, but of course we will also have some time to answer questions after this webinar. Okay, let us start by a very quick question. So since you have registered to this webinar, I guess you are interested in measuring PFAS with combustion IC or have an idea about what this method is. My first question is, if you have experience in measuring PFAS in any way, be it by LC-MS or other technique, please try to find the reaction button and give me a thumbs up so that I can see if anybody has already some experience with measuring PFAS. So if this is possible, yeah, okay, it seems to be possible to raise your hand. That's great. So yeah, and okay, but I don't know whether this is a reaction to my question, but okay. Maybe it's not possible to react. Good. Anyway, let us move on. Hinek, could you check if this is a question or a raising of the hand? I'm not sure.
I think that's probably just raising of the hand.
Okay,
just like a
great.
thumbs up.
Okay, good. All right, so let's start. PFAS analysis. I would like to start with having a look why we are measuring PFAS. And I guess the main topic we have to talk about is that PFAS are anthropogenic. There is almost no natural occurrence of perfluorinated carbon atoms in the nature, but they are actively being produced since 1940, since the 1940s, and there has been wide use. They are very persistent. This is one of the main topics that are bringing them into prominence now, because there is almost no biological degradation in nature. Even if there is some form of degradation, the final products are also more or less always PFAS. This is why they are now, many of them are part of the Stockholm Convention for Persistent Organic Pollutants. And finally, and this is of course also connected, is that there is many potential harmful substances among us. There is evidence for carcinogenic, immunotoxicity effects and effects on the hormones on human bodies, and especially because of the persistence and bioaccumulation, there are also long-term exposure effects that can happen. So this is a reason why PFAS are being observed now quite closely, and why there is so much possible. However, let's have a look. Okay, what is the necessity for some parameters? Well, the traditional way to analyze PFAS is by looking at substances like the ones that we have here, PFOS, they are already being, and PFHXS, they are quite strictly banned already in the European Union, but there is actually thousands more. And this is the point where it becomes interesting, because especially when you, for example, look at PFOA, it is listed with PFOA and its salts and its precursors. So everything that degrades to P4 is also already banished. And these are already thousands of substances. But if you look into the nature, then we also have degradation products. So something that is partially degraded from these kind of PFAS can have a completely different structure that is not even connected anymore. So yes. So this is why, if you look at the traditional way of analyzing results, you will find LC-MS method, where you can find typically 6 to 40 species by single substance analysis, and you can detect them to a very, very low concentration, which is a great thing if you want to detect certain PFAS and you know what you're looking for. But the problem is, if you don't know what you're looking for, there is no way how you can find out how they have been measured. This is where it is necessary to introduce so-called sum parameters that try to find and quantify the PFAS as a group, substance group. Let's have a look how the current legislation is. And if you look at that, there is already several PFAS listed in the Stockholm Conventions. I was mentioning that PFAS itself is listed with its salts. But if you already look at the P4 registration, it says that it is the P4, its salts and precursors. So everything that degrades to P4. And the list of the Stockholm Convention, now the latest update, lists 375 substances that are among this registration. However, if you look at other databases, they can say, okay, even 1,400 substances are actually have CAS numbers that are related and can be considered precursors of P4. So only with this registration within the Stockholm Convention, it says P4 and its precursors, but it actually means more than 1,000 substances. There is also several PFAS listed already within the REACH that are SDHC, and there is a restriction proposal ongoing. There is, for example, also an EU regulation that puts certain levels on foods or eggs or fish for certain PFAS. And then there is, since last year, the new EU Drinking Water Directive. And this is actually the first one which introduces a new parameter that is called PFAS total. And the definition is still vague, but it limits it to 0.5 micron per liter in drinking waters. And then there is another one, which is called sum of PFAS, and there's the limit is even smaller. And if you look into the technical guidance, the difference is the sum of PFAS is single substance analysis, and they are just making the sum of individually determined PFAS, whereas if you look at PFAS total, this is what we are actually looking for as a sum parameter. And then you have countries like France that already started to banish PFAS in certain consumer products starting from next year. So there is a great interest in measuring this. And what I would like to introduce to you is how you would measure this PFAS total, for example, for the Drinking Water Directive with combustion IC. So let's have a look at the instrument, and we were already explaining. This is a joint webinar by us, Nitosec Analytech and Shimadzu, and we will be talking about two parts of the instrument. I will explain to you the first part, the combustion and adsorption unit, together with the sample preparation that is necessary to do these kind of measurements. And my colleague, Dr. Vadim Kraft, will explain to you the IC. And while the IC is looking smaller, it has also a lot of technology inside it. So just because our instrument looks a little bit bigger, it doesn't mean that it's more important. Okay, let's have a look how the combustion IC works and how we can measure total fluorine. The idea behind this is that the only thing that is common for PFAS is that they have carbon-bound fluorine. And this is the species that we want to analyze. So we have a three-step analysis. We have first a combustion, and this combustion converts everything we put in here into HF, gaseous HF. And this is regardless of the matrix that it is in there. So we can measure any kind of products, we can measure environmental samples, whatever. The next step is the absorption. And this is done within our absorption unit. And here we absorb all of the combusted gases into an aqueous solution and convert it into fluoride. And after this, we will have a quantification on the IC for receiving the total fluorine content. And this we can, of course, then calculate back and see, okay, how much original PFAS are we supposed to have in? The specialty of our instrument is that we have various introduction modules, and we know how to prepare samples so that they are most efficiently combusted. And so actually, the point that I would like to stress is whatever matrix you give us, if it's products, intermediates, waste samples, environmental samples, we will have a method to analyze it so that finally the quantification as fluoride is complete and we can measure the PFAS. So let us first have an application for total fluorine, and the most prominent applications here are products. So very prominent is food packaging and textiles. There is already a lot of companies that are going away from PFAS as water repellents, but of course there is still a lot of them in the market, and we need to find out which products have PFAS in them and what kind of PFAS. And then there is also a lot of cosmetics, but also pharmaceuticals and chemicals in general that need to be analyzed if they contain PFAS or any kind of. And as a prominent example, I would like to show you a study done by the Stockholm University using our instrumentation. And what they did is they compared the LC-MS results and compared them to what they found as total fluorine content. And if you look at food packaging, it is almost impossible that there is inorganic fluorine in there. So if you see, okay, they measured 16 different kinds of PFAS, and they found certain PFCAs and PFSAs and PUBs and so on. But even if you make the sum of all of these PFAS, they don't account even for less than 1% of total fluorine that they measured with the instrument. So there is a huge difference between what you can measure with LC-MS on the one hand and combustion IC on the other hand. And all of the rest is actually unexplained. So the question is, of course, is there some interference or so on between the different methods? But what I would propose is that actually there is a lot of unknown PFAS in here, which needs to be examined in more detail. And this is not unusual since there is so many thousand PFAS that are actually currently not quantifiable by LC-MS. So let's have a look for the next step. Now we are looking into PFAS in environmental samples. And here we have a special case, because if you look at the total fluorine, this is what we are analyzing on the instrument. It will consist of organic fluorine, which is most commonly our PFAS, but also inorganic fluorine, fluoride. And because the combustion converts everything into HF, we cannot actually discriminate between this and this easily. So we need some way how we can remove the inorganic fluorine from the matrix in order to be able to say, okay, whatever we measure then as the rest is our PFAS. And there is several techniques to do this, and I would like to introduce to you first the so-called adsorbable organic fluorine. This is a parameter specific for water-based samples. And so this is very well suitable, especially for wastewaters, but also for environmental control. And the idea behind this is that you introduce some separation technique in advance to the combustion, adsorption, and IC. And this method is already standardized. There is a Dean method existing, which is already also ISO draft existing, and we hope that this can be finished in near future. But also there is already a US EPA method that is working on this. And the idea is that you have a sample preparation that involves working on activated carbon, and by this you can have a pre-concentration of the sample and you can separate it. So how does this work? You will have so-called activated carbon columns with a specific diameter and a specified amount of activated carbon on it. And you will add your sample onto this. This is typically done with 100 milliliters of sample, because here we know the adsorption properties quite well. And this will lead to all of the organic substances being adsorbed onto the activated carbon. As a second step, you will use a washing solution and wash off all of the inorganic fluorine. This is the separation step. The organic stuff stays back on the activated carbon, and the inorganic is flushed out of the carbon column. And then you simply use an instrument to measure this. And this is the second instrument I would like to show you today. So here you can see the Shimadzu IC. You can see the absorption unit that I also showed you before on the other slide. But this instrument is called the AOX400. This is dedicated for AOF analysis because it has a very special sample introduction technique. And the key point behind this is I was showing you this kind of activated carbon columns, and you are absorbing your sample on here, and typically your sample contains several nanograms of PFAS, so not more. And so there is a huge risk that if you transfer this into some other form of combustion vessel, that there is cross-contamination. And to avoid this cross-contamination, the easiest way is that you do this absorption and then simply put this column on top of our autosampler so that it is automatically injected into the furnace. This is a system that is not only very reliable, but it is also very easy to automate and can therefore measure a lot of substances straightforward. And what you can see is if you do this kind of measurements is that when we measure different kinds of PFAS, for example, PHFAXS, P4 and PFOS as the main ingredients, that you can get good recoveries over the typical concentration range between 0 to 100 ppb, which is the typical operation range for the AOF. Unfortunately, this method is not yet suitable for drinking water samples because the measurement range and the limits that I was showing you are below the operating limit of this method. So there is some research ongoing, but I will show you about this a little bit later. As an example, I would like to show you work by some colleagues in Wiesbaden, and also they did some comparison where they measured over 1 year and compared the AOF results with LC-MS measurements. Here they measured 14 targeted individual PFAS, and similar to the results before, what you can see is that there is a significant discrepancy between the sum of PFAS that they could analyze with LC-MS and the AOF values that they measured with the CIC. And I think especially for this kind of environmental control, it is very useful to use this kind of analysis parameters to get an idea, okay, where do we have actually the highest contaminated samples? Because if you look at this one, this has almost 0.5 milligram per liter of something inside it, whereas the individual analysis showed it, okay, it's quite similar to the ones that have the lowest contamination. Finally, let's have a look at the extractable organic fluorine. This is a method that uses liquid organic matrix finally to get there, and there is also SPE methods. So this is SPE, I think, is extraction method that is quite well known, especially for the LC-MS sample preparation. So the SPE is quite similar to this, but there is still a lot of research work necessary to go on. And there is many different extraction methods, and depending on the matrix, you have to choose different methods to make it work. For water-based matrices, the SPE-OF is quite well established. And actually, this is the one that is probably also being applied for the drinking water in the future. But there is also still a little bit missing data. So for example, if you look into a very small round-robin test for EOF and waters, so what they did is they measured some ultra-pure waters that were spiked with PFAS and some groundwaters that were spiked with PFAS, and they had 3 different laboratories. And while they could measure more or less in a similar range, it is also quite difficult to get comparable results. So here you could see that one laboratory was higher on this respect, whereas on other samples, the other laboratories were higher. So there still needs to be some research done so that we can get comparable results. As a summary, I would like to say, okay, depending on your sample, there is many different possibilities how we could try to analyze PFAS. And that combustion IC, in my opinion, is a very good tool to measure the total fluorine content. And if you have derived parameters that then start to separate between inorganic and organic and try to extract as much of the PFAS of the matrix as necessary, then you can achieve more or less all of the necessary analytical requirements. So this concludes my presentation. I thank you very much for your attention, and I'm now very much open to questions.
So thank you again to Takuro, and I will pass words to Dr. Kraft. So please, floor is yours.
Okay, thank you very much. Now I'm opening my presentation. I hope you can see it.
Yes, we can see it.
Perfect. So I will directly answer the question, can we do the in our system? Yes, we have. And actually, I will also explain in more details about this option in our ion chromatography systems. But before we start, I would like to briefly outline the history of Shimadzu's liquid chromatography instruments, specifically focusing on ion chromatography. It began 45 years ago in 1978, leading to the introduction of the first ion chromatography instrument a few years later. At the start of the century, Shimadzu IC was coupled with a combustion system developed by Mitsubishi Chemicals. Over the past decade, Shimadzu has introduced a new technique, supercritical fluid chromatography, abbreviation SFC, alongside the launch of the Nexira series, which represents the latest Shimadzu's LC instruments. Among this innovation is the new ion chromatography system, which, along with its integration with the nitrocycle combustion instrument, is the focus of our webinar. And here's the outline of my presentation. I will start it with a brief introduction to the basics of ion chromatography. How does it compare to HPLC? What is the separation mechanism? Why can LON separation be advantageous? And how are the compounds detected before introducing the new HICSP ion chromatography system? I will talk about the lab solution software to control our instruments, and then I will talk a little bit about columns choices in ion chromatography. And after, I will sum it all up in a final slide. So I believe we are all familiar with liquid chromatography technique, and is it as a method for separating and quantifying analytes and mixtures. This principle is applicable for ion chromatography as well, which also utilizes a liquid chromatography, a liquid and a stationary phase to separate the analytes of interest. In HPLC, the target analytes are primarily organic compounds, and separations is achieved through interactions between the analytes and both the mobile and stationary phases. These interactions may involve hydrophobic forces, dipole-dipole attractions, and occasionally steric effects. Ion chromatography operates similarly to HPLC, but is specifically designed for analyzing inorganic ions. In IC, the stationary phase consists of an ion exchange resin, while the mobile phase, typically called the eluent, it is usually an aqueous buffer with adjusted pH. Separation occurs through the exchange equilibria between ions in eluent and those ions attached to the resin surface. An IC system, like any HPLC system, includes a pump, an injector, a separation column, which is often installed in the column often, and a detector. The column in ion chromatography contains either ion exchange or ion exclusion resin, and the detector is generally a conductivity detector. An ion suppressor may also be employed to enhance the detector sensitivity. This is specifically interesting for anions. In IC, the analytes of interest are ions, species that dissolve in water and carry an electrical charge. For instance, dissolving table salt in this example, sodium chloride in water produces sodium cations and chloride anions. And the suppressor effectively improves the detection signal for the anion of interest by not only reducing background noise through the replacement of sodium ions with hydrogen ions, but also increasing the peak intensity for the analyte. Now let me introduce the HIC-ESP ion chromatography system. Here we see a flow line of the system. As mentioned before, the IC is an HPLC instrument comprising a solvent pump to deliver the eluent, an autosampler for sample injection, a column, often housing the separation column with the ion exchange resin and the detector flow itself. And the Shimadzu ICDS-40A anion suppressor is placed after the analytical column and before the detection cell. And the waste liquid then moves back through the suppressor for continuous online regeneration. This is typical electrolytic suppressor. This schematic representation illustrates the structure and operating principle of the ICDS-40A anion suppressor from Shimadzu. Since the ion suppressor must be placed between the column and the detector's flow cell, the internal volume of the suppressor can influence the peak shape. And the folded membrane structure of our suppressor results in a small well volume, minimizing peak dispersion while ensuring high exchange efficiency through multiple layers of cation exchange membranes from the suppressor. The eluent after the column is rich in sodium ions, which flow towards the cathode, while hydrogen ions produced by water electrolysis replace the sodium ions in the eluent from the column. In a second pump for the electrolysis of water, the ICDS-40A suppressor utilizes the effluent from the detector in a recycle mode, as it was mentioned before. The features of the electrolytic ion suppressor ICDS-40A include sharp peaks that enhance sensitivity due to its small inner volume and unique multi-layer membrane design. As an electrodialysis type suppressor, it is user-friendly and operates with continuous online regeneration, eliminating the need for hazardous regeneration solvent, which saves both time and money. Here we see an example of why a reduced dispersion volume is critical for certain analysis. The chromatogram demonstrates improved separation between the negative peak of water, you can see it here, and the first eluting peak. In this case, it's the fluoride ion. The sharp peak of fluoride shows a 1.2 times increase in response compared to another comparable electrolytic suppressor. This highlights how the new suppressor design enhanced the conductivity detection by providing low background signals and increased peak height. This feature is specifically interesting in sensitive analysis of PFAS by CIC, focusing on the determination of fluoride ion. The HIC-ESP ion chromatograph is built on proven Shimadzu HPLC hardware, ensuring high precision solvent delivery. Minimizing pressure pulsation is crucial, of course, and as electrical conductivity detection is sensitive to pressure changes that can introduce noise. The pump features an optional plunger reset mechanism that significantly enhances the lifespan of pump seals, resulting in greater robustness. Our autosampler enables high accuracy, high-speed injections ranging from 1.1 microliter to 2 milliliter. Also, ultra-low carryover is achieved through extensive autosampler rinsing options, and the sampler offers precise sample injection with excellent repeatability. Additionally, the direct injection principle of our autosampler allows for variable injection volumes without the need for installation of dedicated sample loops. So you can inject from 0.1 to 2 milliliter injection volume without installation of sample loops. The slim forced air circulation column oven guarantees precise temperature regulation and can accommodate different columns lengths up to 30 centimeter length. The suppressor is integrated into the upper part of the column oven, while the temperature regulation detection cell is placed in the heated area of the oven, which supports accurate temperature control. This design minimizes detector noise and results in a stable baseline in conductivity detection, which is sensitive to temperature fluctuations. The instrument is also equipped with a high-performance online degassing system to guarantee stable analysis. Furthermore, with its modular design, the system also supports other detector options, such as UV or PDA, which can be beneficial for more selective or more sensitive determination of ionic nitric compounds or iodide ions in CIC analysis. Here you can see two chromatograms showing suppressor conductivity and UV detection. The detection with both detectors is simultaneously possible because both detectors can be connected in series. Another aspect of the system is its compact size. And we know that many laboratories have limited place and are interested in slim instruments. The Shimadzu ion chromatography system is only 42 centimeter wide, which is approximately half the size of comparable IC systems on the market. Depending on the specific application, the customer can choose a standalone IC instrument suitable for the standard IC analysis with an autosampler. The same system can be also connected to a combustion instrument. It is not required to order an LC or IC controller. In addition, you can order just a CBM40 Lite, very small controller unit, which can be installed on the back side of the pump. As mentioned before, the suppressor is placed in the non-heated area of the column oven. And additionally, a system configuration without the IC autosampler for online CIC analysis is feasible as well, of course. And you can also upgrade the system with UV detection if required. So now I will speak about our lab solution software, and because the control software is a significant component of the system performance. So all Shimadzu instruments, including LC, SFC, LCMS, GC, GCMS, TOC, and even testing machines are managed through lab solution software. We offer both file-based database or client-server software options compliant with regulatory requirements. Lab Solutions features an intuitive, user-friendly, and customizable interface for data acquisition, post-run data management, and reporting. And this is what the real-time LC control window in the software looks like. On the top, we have a variety of shortcuts, icons that can be customized to enable the most frequently used actions immediately. In the navigation bar on the left side, you can toggle between instrument parameters and data analysis, as well as start and stop a single run. large window display a chromatogram view to monitor the analysis. In addition, all instrument parameters can be checked in another window, and methods can be created from here. A nice feature is the quick batch function, which enables the fast creation of a longer analysis sequence, including standards, unknowns, and control samples. This template allows for automatic generation of the entire batch table by specifying the method, sample type, and a few other necessary parameters. Thereby, it can help to reduce manual steps by batch table creation and to minimize the risk of errors. Additionally, the report function can be integrated into the batch file, simplifying and automating the analytical workflow. It enables the automated creation of individual analysis or summary reports, and as well as multi-data reports, including graphs and data processing for multiple samples. The data can be automatically imported into a predefined template, minimizing the time needed for report preparation and reducing the risk of human errors. Oh, something is happening. Can you see my screen still?
Yes, we can see your screen. Yes.
Okay. Great. Now I will speak about our columns. Shimadzu provides a variety of columns for ion chromatography applications, both with and without ion separation. And the choice of columns depends on the specific separation challenge, of course, which leads us to the different application areas of ion chromatography. You can find additional information on our webpage directly from this link. And what is interesting for our CIC analysis are these columns. So we have the Shimpac ICSA2 column, which has 9 micrometer particle size, and we also have the Shimpac ICSA3 column if you will require high resolution in your analysis. So please visit Shimadzu homepage for application examples and CIC analysis, which is the homepage is continuously updated with examples. And please also ask your local Shimadzu sales representatives. Okay, to summarize, the Shimadzu HIKSP ion chromatograph features a newly designed electrodialytic anion suppressor with minimized internal volume, offering optimal peak shape and effective separation of early eluting ions from the water dip. It provides more stable performance than cartridge type suppressors, and it is cost effective and easy to handle due to its online self-regenerating ability. The proven, robust, and reliable Shimadzu LC equipment is available in a compact and slim design, saving valuable space in your laboratory. And with this, I thank you for your attention, and should you have any follow-up questions, please don't hesitate to ask, of course. Thank you very much.